You have just had a good exposure to the various fundamental heat transfer science and an indication how that science of heat transfer is used for axial flow turbine cooling. In today's lecture, we will be looking at the technology of gas turbine cooling. Now, cooling of axial flow turbines, especially in aero engines, have been in vogue for nearly 50 years now. So, the cooling technology is indeed 50 years. It did not start with cooling technology. Axial flow turbines in the early era were without cooling technology. However, for nearly 50 years now, various kinds of cooling technology have been used, and we will look at this entire generations of cooling technologies in today's lecture. In fact, all kinds of those cooling technologies are still in use today, because you need some of those cooling technologies even today in simple gas turbine engines, whereas a more modern or more ambitious high performance gas turbine engine may require a more advanced cooling system. So, if you are creating a simple gas turbine engine, old fashioned cooling technology would still be useful, and hence those technologies are still in use in some form or other in many gas turbine engines, especially in aero engines even today. So, we will look at all those technologies that have developed over last 50 years. Now, as I mentioned, the cooling technology is based primarily on the science of heat transfer. The idea of cooling actually came from the gas turbine thermodynamic cycle analysis, which very clearly showed that if you can increase the turbine entry temperature, you would get a substantial benefit in terms of the work done by the cycle, which of course, in terms of gas turbine engine means more work done by the turbine, more work available either for creation of thrust for aero engines or for running a propeller which creates thrust, or for land based application. It simply means that you can get more power output out of the single gas turbine engine. So, those fundamental science of thermodynamics finally bore down on the fact that you need to have cooling, because the material science was unable to go beyond a certain level to provide material or alloys, metal alloys that could withstand temperature beyond a certain limit, which is roughly of the order of 1000 degree K. Now, beyond that, it became very apparent that ordinary material technology is not going to really be really greatly helpful, and in which case additional techniques are required if you want the turbine entry temperature to go even higher. And that is when the cooling technology came in, and of course, the entire field of heat transfer had to be utilized. So, in today's class, we will look at the technology. In the last class, you had an exposure to the science of heat transfer, and we have done all the aerodynamics that is necessary on axial flow turbines. So, in today's class, let us take a look at various kinds of axial flow turbine cooling technologies. Now, much of this cooling technology does indeed involve a lot of engineering. You will see that a lot of things are engineered in. Science of heat transfer creates the basic fundamental basis. As I mentioned, the thermodynamics showed us the way that you need to have high turbine entry temperature, which then requires cooling, which uses the science of heat transfer. And then there is a whole lot of engineering, the thermal engineering, the mechanical engineering, the manufacturing technology, all that comes into picture. And we will have a look at some of these technologies in today's lecture one by one. Let us take a look at what are the fundamental issues involved and how the whole thing has developed over a little more than 50 years. If you look at the graph which is available in many books probably easily see that in the early era in 1950s or so, most of the blades were actually uncooled blades. So, but they could take up to about 1000 degrees centigrade or so, and then from there onwards, if you are aspiring towards higher turbine entry temperature, you have to resort to some kind of cooling technology. Beyond, otherwise the turbine inlet temperature could not be improved upon, and irrespective of what material you use, the material technology was not quite helping the matters. So, simple cooling technology was used, in which a certain amount of cold air was indeed passed through the blade. This provided a little bit of cooling of the order of 25-30 degrees to begin with, and that was quite often sufficient to raise the temperature by 50 degrees or thereabouts, and slowly the temperature started rising as the cooling technology improved upon. It is basically an engineering method coupled with the heat transfer, science of heat transfer, and as a result of which the temperature could go up to near about 1400 degree or so. And then of course, people realized that you need more complex cooling technology to go higher up, and hence more complicated cooling technology came, which we will be talking about in today's lecture. And hence more sophisticated cooling system came in, which involved film cooling, and then impingement cooling, so on and so forth, which has taken the turbine entry temperature to near about 2000 degrees. So, very modern gas turbines do have turbine entry temperature very close to 1900 or 2000 K. However, the material, as I mentioned, the material technology has not really helped matters a great deal over here, and the projected trend that was shown earlier, and by now we should have reached values of the order of 2200 or 2300 degree K, that has indeed actually not happened. And one of the reasons is some of the cooling technologies that were projected, and we will be talking about it in, for example, transpiration cooling. Those kind of cooling technologies have not matured. One of the reasons again is the material technology. The new material, the porous material, which was to facilitate transpiration cooling, has not really happened, and as a result of which the cooling technology did not project beyond what is shown here, and this projected development not really quite matured. There is a lot of research still going on, and we are not quite as yet crossing the 2200 K mark in actual commercial applications. So, that is where we are. We are near about 2000 or so, and that is good enough for us actually to use in most of the modern gas turbine engines. And we shall see that since the pressure ratio has gone up, the efficiency of the turbine has been actually upgraded hugely through upgradation of compression ratio, and this upgradation of turbine entry temperature coupled with the high compression ratio has given gas turbine engines huge efficiency boost, and in terms of fuel saving, there is a huge fuel saving in the modern engines. So, turbine entry temperature boost actually is known from fundamental thermodynamics to give better and more efficient engines and provide more power. Now, if we simply summarize the whole thing, in the 50s the blades were uncooled, the early era of gas turbine engines, and as a result the temperatures were somewhere around 1000 to 1100 K. And then of course, the cooling technologies came, which were internal 1 or 2 pass cooling. We will look at this 1 or 2 pass cooling very soon today, and the temperature could go up to about 1200 to 1400 K, that is about 150 degree more where possible with cooling. Later on, the cooling technology developed into internal convection cooling, which allowed a lot more coolant to be used and lot more elaborate cooling system, and temperature could be pushed to 1300 to 1500 K. And then came of course, the film cooling towards the end of 70s, which existed along with the internal convection cooling. So, film cooling plus internal convection cooling pushed the turbine inlet temperature to higher than 1600 K. And then of course, the impingement cooling matured, the idea of which has been around for a long time and has pushed the temperatures now to close to 2000 K. Thereabouts, the whole thing has kind of stagnated a little, because the transpiration cooling has not quite matured. It has been, as an idea, it has been around for nearly 50 years. It involved microchannel cooling methodology, the science of which is well known, but the technology is not quite available as of today. And the porous material that can withstand the stresses in a turbine blade has also not quite matured as of today, to the best of our knowledge. So, the turbine technology has matured hugely over a period of 50 years and has resulted in engines that are more powerful and of course, which are indeed smaller in size. Now, when we talk about turbine cooling, the first thing that comes to mind is what are you cooling? You see, the turbine is processing gas which is hot and of course, high pressure, but the blade feels a temperature. The feeling of the blade here is the important issue. The blade feels a temperature which is not same as the turbine entry temperature. So, if the turbine entry temperature is T 01 and the blade exit temperature is T 02, what the blade would feel is an average of the two minus the rotating kinetic head, which is shown as u mean square by twice C p of the gas which is passing through, plus the degree of reaction factored in here. Now, this gives rise to the situation that the blade temperature as felt on the blade surface, average blade temperature, is something quite different from the gas temperature. So, gas temperature is not what the blade feels. The blade feels a different temperature arguably, and as is quite obvious here, it will feel a temperature lower than the gas temperature. So, the requirement for cooling is not with respect to the gas temperature, it is more with respect to what the blade actually feels. So, that is the temperature that has to be cooled through cooling technology. The science of heat transfer that you have done in the last class, we can simply bring in here the fact that the heat transfer coefficient is equal to the quantity of heat to be transferred at any local point on the blade surface at the location of the blade, which is normally given chord wise in terms of often x by c on the chord, and the local surface area over there. The temperature differential between the hot gas and the surface, as we have just seen, the blade surface temperature is indeed less than the hot gas temperature, and it will vary from the local point to point on the blade surface, and then of course, the time that is required to effect the heat transfer. Quite often the heat transfer is expressed, as we have done in the last class, in some detail in terms of Nusselt's number, and they are known to be proportional to Reynolds number and Prandtl number. This is also a semi empirical relationship which has been developed essentially for simple systems like flat plate, and Nusselt's number is directly relatable to Reynolds number and Prandtl number for simple systems through some constant terms which are used to create this semi empirical relationship. Now, this is the kind of science or technology that one would need to bring forth in the turbine cooling business. Now, let us look at the technology. What happens is, when you have a blade, this is a typical turbine blade, and you are looking at a diagram which probably you had a look at in the last lecture also, but let us discuss this again. The flow comes in here, and at this point you have the leading edge, which is the stagnation point. Now, what happens at the stagnation point? The flow comes to a halt. when the flow comes to a halt thermally, that place the total temperature is equal to the static temperature, which means this point of the blade feels the entire total temperature of the gas flow. That means, the static temperature plus the kinetic head that the gas is carrying, the entire thing is felt over here at the stagnation point. So, the stagnation point is indeed the hot spot, the hottest spot on the blade surface. As the blade picks up speed, it actually drops off the temperature, and then through the transition from laminar to turbulent flow, as the it flows over the gas blade surface, the gas actually accelerates. As it accelerates, the local temperature, the static temperature, remember, is the static temperature that blade would be indeed feeling. So, the local static temperature starts falling off. So, as you have expansion or acceleration over the blade surface, the static temperature indeed falls off. However, as you are aware, aerodynamically towards the trailing edge, there is another possible stagnation point depending on the flow situation, and somewhere on that stagnation point you would again feel a hot spot. So, the flow again would feel the full temperature field over there, that is static plus kinetic at that point. Same thing happens over the pressure surface. So, the temperature, there is a continuous variation of temperature. So, just like pressure, you can see that as the pressure varies over the blade surfaces, the temperature also would vary over the blade surfaces, and in a turbine this variation is huge, unlike in a compressor where the pressure varies hugely, but the temperature does not probably vary so much. In turbine, the temperature would vary hugely. Now, as you have done in the last class, as the flow transits from laminar to turbulent flow through the transition, the heat transfer from the hot gas to the body of the blade is facilitated, which means there is more heat transfer across the body of the blade. As a result, the blade would actually be getting more heated towards the rear part of the blade, where the static temperature may be falling off. Here, the blade is probably somewhat shielded by the laminar layers, and as a result of which the blade feels lower temperature, even though the temperature outside is actually much hotter. So, near the leading edge, temperature outside is much hotter, but the blade feels less, but later on, even if the temperature is falling off, the blade actually is made to feel much higher temperature on the blade surface, because the boundary layer outside is turbulent boundary layer. So, with this knowledge, if we can move towards the technology. Now, what happens is, as we were discussing, we have a hot spot on the leading edge, you have a hot spot at the trailing edge. A simple aerofoil is being shown here, and you have a huge temperature gradient on the chordwise direction on the blade surface on both the surfaces. In a real turbine, the two surfaces are unequal. What is simply done is you create blade passages, internal passages, through which cold air is passed, let us say from one end of the blade to another, which is from hub to tip. Now, the first row of blades is of course, the stator, which is fixed at both ends. So, you can indeed pass air from hub to tip or tip to hub, cold air, and then that cold air would convect away, carry away heat. That heat has to first conduct itself through the blade solid body from the surface into this cold air, and then the cold air would carry away the heat on a continuous basis. So, there is a continuous conduction across the solid body of the blade surface, and then continuous convection by the cooling air, which is passing through the passages on a continuous basis. So, there is a continuous requirement of cooling air when the gas turbine is operational. So, this is a simple method by which the cooling technology was inducted into the gas turbine cooling. If we look at a little more elaborate system, this is a CFD plus ANSYS simulation, and it gives an idea about the kind of temperature profile you have in a typical gas turbine blade and what you would require to do cooling. You have a hot spot here, you have a hot spot around here, the trailing edge is very thin and is very difficult to provide cooling over there in terms of internal passages. So, these are the internal passages. As you can see here, the shapes have evolved to not only allow more passages in a distributed manner. So, you have more distributed passages, also you have more control over the amount of coolant passing through these passages. So, you have more control over what is happening. So, this is one passage which is, let us say, cooling more near the leading edge area, which as we discussed is the hot area, and then there are distributed coolant passages. So, that the cooling is distributed over the blade surfaces from both the surfaces. So, this is a real blade that has been fabricated, and one can see that these are the various kind of passages that have been created through modern fabrication technology in a high temperature material. Remember, turbine uses high temperature material. So, making such passages is requires very modern manufacturing technology. The upper plate that you see actually is a forged blade, where these passages were created and the blade was made by forging, and the passages which were before forging looked something like this, and once the blade is forged into the shape, the passages take these shapes. However, this blade is fabricated, that means these passages are machined in high temperature material, which requires very high modern fabrication technology. Now, what we see is that the blade temperature may vary along the blade surface from leading edge to trailing edge by almost 200 to 300 degree K. Now, that is a very large variation to cater to, which means that temperature over here or over here may be 200 to 300 degrees more than the temperature over here, and the temperature is varying all along the blade surface. Now, this requires cooling technology, which would cater to the amount of cooling required here, the amount of cooling required here, here and here. So, that is what we were discussing, that the amount of coolant to be used here, over here, over here, and then near the trailing edge over here would indeed vary substantially depending on the blade shape, depending on the temperature at which it is operating, and of course, depending on the cooling air that is made available. Now, all this needs to be calculated very accurately. This accurate calculation is where engineering and heat transfer science comes in very strongly. You need to calculate very accurately what is the amount of air going into each of those channels. And as you can see, the shape of the channel, the size of the channel varies depending on where the channel is located on the blade. Now, this requires that you have a very accurate method of calculating how much cooling air is required where. Okay. Now, as we can see here, the temperature and the heat requirement, cooling requirement varies substantially. So, this needs to be very accurately calculated. So, and then of course, as you can see, you have the technology in which these shapes are created. So, now these shapes carry a certain amount of cooling air, and as you can see here, this has been created. Finally, it will exit through the trailing edge. As I was mentioning, trailing edge cooling is a problem, whereas the trailing edge, it is known is a hot spot. So, the modern method has created facilitated a process by which the cooling air finally may exit through the trailing edge, cooling the trailing edge itself. So, those are the various technologies that have to be brought into in the turbine cooling business. So, as we were saying that the blade temperature also may vary from root to the tip of a rotor. Stators by design, as we have seen, may be kept untwisted, but the rotor may have a little bit of twist, and that will give rise to temperature gradient from root to tip. So, that again needs to be factored into this very accurate cooling technology that we need to incorporate in modern axial flow turbines. Now, maximum temperature is felt at the leading edge of the first stator as the flow just comes from the combustion chamber. So, the first rotor is first stator is what requires the best of the cooling technology if you have to increase the turbine entry temperature. Now, we will talk about more modern cooling technology as we go along today. The HP turbine blades, both the stator and the rotor, face maximum temperature across the rotor and the stator. So, almost all modern aero engine HP turbine blade, stator and rotor are cooled. In the early era in 60s, only the HP stator was cooled, but later on both rotor and stator are cooled, and in today's modern aero engine HP turbine first stage as well as second stage are most likely to be both rotor and stator are likely to be cooled. Now, there is another issue here. The blades are thermally loaded in cycles of operation. Now, this essentially means that you have a situation when the gas turbine starts operating, the turbine gets heated up, it goes to full temperature, and then it operates at full temperature during, let us say, when the aircraft is flying from takeoff to climb, and then it goes to cruise. Now, when it goes to cruise, as you know, the turbine is actually brought down to lower temperature level, lower speed level, lower rotating RPM, and hence it is operating at a lower temperature. Then after some time, the turbine the engine is brought down to lower operating speeds. Slowly the aircraft comes down, it touches down and it comes to a halt, the engine is closed down. So, the turbine is heated up, then it is cooled down, operates in slightly less heat condition through the cruise, and then it is shut off. So, the turbine is continuously going through this cycle of temperatures. For a long period of time, when the engine is not operational, it is a cold turbine, it is just static. When the engine is operational, it goes through heat cycles or very high cycles. If it is a military engine, it is going through very sharp transients, very high temperature sometimes, not so high temperature some other times. So, it is going through cycles of temperatures, and then again when the engine is grounded, the aircraft is grounded, it is cold. So, the material of the turbine is continuously being treated to high temperature and then for long period of time to cold state of static operation. So, this gives rise to the fact that the turbine is treated to cycles of temperature. So, many of the turbine failures occur in this fatigue failure, which is due to this cyclic loading of the blades. Now, remember, turbine is also rotors especially getting highly loaded due to the aerodynamic loading. The aerodynamic load is huge when the gas is flowing past the turbine blades. So, this aerodynamic load is now compounded with the thermal loading, which as we have just seen changes from leading edge to trailing edge, from root to tip. There is a continuous variation of temperature on the blade surface over the entire blade of the turbine. Now, this gives rise to temperature gradient, the loading pattern changes, and when coupled with aerodynamic loading, it gives rise to very complicated loading pattern and very complicated stress pattern, which as we see now actually goes through cycles of operation, depending on whether the turbine is operating or it is grounded and static. The result is the turbine failure often occurs in creep, mainly due to this thermal cycles. So, creep is a fatigue failure due to cyclic operation of the gas turbine engines. So, the failure of the gas turbine often occurs in creep, which is the thermal fatigue kind of compounded stress that occurs, and mainly due to the thermal fatigue. The compressor blades, for example, do not fail in creep, they fail mainly in loads during operation. Those blades of course, are much thinner. The turbine blades are much thicker, as you have seen, but the thermal load indeed creates a lot of problem. So, even though turbine blades are thicker, they are made of high temperature material, even then the life of a turbine blade is indeed often much less than that of a typical compressor blade. So, this is a huge problem in terms of life of turbine blades, and of course, the cooling technology helps the matter. There are many blades where if you do not apply cooling, actually the blade would get charred in a matter of few minutes. Whereas, if you apply cooling, the blade would last for thousands of hours of operation. So, the difference between cooling and not cooling a modern gas turbine makes a difference in life of turbine blade by thousands of hours. If a gas turbine entry temperature is of the order of 1600 or 1700 degree K, and if that blade is not cooled, rest assured that blade will get charred in a matter of few seconds. Okay. So, that is the difference between uncooled blade and a cooled blade in modern gas turbine applications. So, that is where the cooling comes in. Let us take a look at the situation. If you have a typical turbine blade, and if you have this kind of let us say very simple cooling passages, so many of them, 1 to 16 of them, they have to run through the entire length of the blade of a turbine blade from root to the tip. So, typically the air would be brought in from compressor, compressed air would be brought in through the root system. You have the fir tree root fixing system here, it comes in here, and then it gets into these passages. Okay. You can have so many passages, or you can have 4 or 5 passages, as we have seen in the earlier slides, and they all then go through these entire length, cooling the blade at different places in a differential manner. On the right hand side, you just see a research output of internal temperatures as captured in a French laboratory, and you can see the kind of temperature profile that you get. Some of the internal temperatures are very high. Here the internal temperature is somewhat less, because as we have seen, the flow around here is laminar in nature, and as a result the blades do not feel so much. Somewhere over here the blades become the outer surface, the flow becomes turbulent. Once it becomes turbulent, the hot gas temperature flows inside very quickly, and then the blades start getting hugely heated up. So, the cooling requirement indeed here is more, even though the temperature near the leading edge is actually more. So, this aerodynamics actually facilitates the heating of the blades around this area, and this is where you indeed require more cooling, and that is why most of the cooling technology in the early era in 60s and 70s and indeed in 80s, the cooling was mostly being done in this area. Okay. But of course, we know, and we will see today, that more and more modern cooling is available near the leading edge as well as near the trailing edge. As the temperature has gone up, you need to indeed cool the entire blade. Let us take a look at the cooling technologies, the fundamentals of the cooling technologies that we are talking about. We mentioned that the cooling is done by internal convection cooling, which essentially means that you have so many passages, and through them the cooling air is passed. This is, let us say, the blade surface or the solid body of the blade. Inside of the solid body, you have so many cooling passages through which cooling air has to be passed on a continuous basis, and outside you have the hot gas. A variant of this is that the cooling air is blown into the inside surface of the outer shell of the blade. So, the blade is made of a shell, which is a solid body of course. Inside you have another shell, inside of which you have the cooling passage, maybe a common cooling passage, which has holes. Now, these holes allow the cooling air to come out and impinge on the entire inner surface of the outer shell, and this is called internal impingement cooling. And if you do that, the entire internal surface of the outer shell is cooled on a continuous basis through internal cooling system. So, this is simply called internal impingement cooling, and we shall see this is how the leading edges of most of the modern turbine blades are actually cooled. The other method is simply called film cooling. Now, the kind of method that we saw through the internal cooling has their limits. Once those limits are reached, you need more explicit and more active cooling system. So, the cooling air itself is now brought out, it is not inside anymore, you need to bring it out, and then this cooling air is brought out through holes, and these holes ooze out the air and then create a film on the blade surface. So, on the blade surface you create a film of cold air, and then this cold air provides a cold film, which means it submerges inside the boundary layer on the outside of the blade surface. So, you have a cold boundary layer on the blade surface. If you provide a distributed holes on the inside the blade, so the through various holes the internal cold air is brought out and is injected out onto the surface to create films of cold air on a continuous basis over the entire surface of the blade. Now, if you do that, you have a continuous cold air. Now, what happens is, if you for example, brought out cold air over here in the first hole, by the time it reaches some distance, that cold air would get mixed with the hot air, would become hot. So, you need to bring out cold air again, which would again then become hot after a little distance. So, you need to bring out cold air every short distance over the blade surface to keep a continuously flowing cold boundary layer on the blade surface. Now, remember, we want a cold boundary layer. We do not want this cold air to eject out like a jet into the hot gas. That would interfere with the turbine operation and would adversely affect the turbine working. So, the work done from the turbine would go down very sharply, because the basic aerodynamics that we have discussed in detail would then be badly affected by this cold air. We do not want that. We do not want the cold air to eject out of the those cooling holes in a stream of jets and get into the hot air and interfere with the hot air operation, which is a different operation. The hot air is flowing over the turbine, it is giving up energy to the rotating turbine blades, it is doing work, transferring work onto the blades are rotating and creating mechanical energy. All that would be adversely affected if you allow this cold air to eject out like a jet. We do not want jets, we do not want cold jets, we want cold air to just come out very gently through the holes and create a film on the blade surface. Then we have a film cooling. So, the boundary layer which we saw was becoming turbulent boundary layer. Subsumed inside that boundary layer would be this cold air, and this cold air would create some kind of a insulation between the hot gas and the body of the solid body of the blade. So, this is how the film cooling technology actually works. If you can do that correctly, you have a very good cooling system. If you can't do it correctly, you are going to be affected by your turbine work. Now, the transpiration cooling, which people have been talking about for 50 years now, actually involves that you have a porous solid body or outer shell of the turbine blade. So, you have cold air oozing out like perspiration through this solid body of the blades to create continuous film cooling. Now, this is of course, the ultimate ideal of film cooling. You just allow the air to go inside the turbine blades, inside the blade passage, internal passage of the blades with some pressure, and that pressure will drive the flow out through this pores. So, it is a porous body, and through which it will create it will just ooze out. Again, there is no jet to be brought out. It will just ooze out and create a film on this surface to create a cold film on a continuous basis over the entire surface. Now, this is much the same way we actually perspire, and our body sort of gets cooled when the perspiration actually evaporates from our skin. So, it is the same concept. However, what has happened is, over the years, this porous technology, porous medium that is required to make the turbine blades has not quite matured to date. It cannot take the strength, as we have just discussed. Turbine blades need to be very strong to withstand the aerodynamic loads, to withstand the thermal loads. Otherwise, the life of the turbine, as we have seen, can be in a few seconds. So, the porous material that we use need to be strong enough to withstand all those cycles of temperatures and gas loading and work for thousands of hours, preferably 10, 15, 20,000 hours. That has not happened, that material has not come through, and as a result, the transpiration cooling has not quite matured to date. So, we have the film cooling, in which you need to very accurately calculate through each hole what should be the amount of air coming out through this hole, what should be the dimension of each of these holes depending on where the hole is on the blade, and then of course, the pressure ratio across this particular hole, because the pressure ratio will drive the flow from inside to outside, and it should be just sufficient for the air to come out and create a film. If the pressure ratio is too high, that means, if the internal pressure by some chance is much higher than the outside pressure just over here, the air will eject out like a jet, and as we just discussed, that is most unwanted. So, we need to create a pressure ratio at each of these holes exactly as much as is required for the air to come out at this particular location and just create a film. As I mentioned, this requires very accurate calculation and very accurate estimation of what is happening gas dynamically and thermally over the turbine blades. Now, let us look at some of the details of the technology. As we can see here, we have a system. Let us look at the bottom. You have one single channel through which the air is internal cooled air is being brought in, mainly from the compressors, compressed air, and then this common airflow channel is indeed making air coming out through various holes. It cools the inside surface, it cools the entire surface, and finally, it comes out from the trailing edge, cooling the trailing edge as well. So, it cools the inside surface by impingement, internal impingement cooling. So, the entire inside surface is being cooled by internal impingement cooling. Whereas, here we have holes. So, impingement cooling is used at the leading edge to cool the leading edge, which as we mentioned can be a hot spot, and then of course, it cools the other surfaces through internal cooling system, and then again here we allow the air to come out through the trailing edge, in the process cooling the trailing edge also. You remember after it cools the internal surfaces, the cooling air itself gets a little hot. However, as we have just seen, the trailing edge is really very hot, and compared to that, this internal air is still cold. So, all you require is air that is colder, substantially colder than the outer hot gas, and it still can do a little bit of cooling. You do not need very cold air here, you need air that is a little colder than what is outside. Now, this is a picture of a full blade film cooling. We have so many passages, separate passages through which air is brought in. Here in this picture, you have two large passages. In the picture over here, you have number of passages, each of which caters to one hole or two holes, and through which air is brought out, and each of these holes then create a little bit of film over here. It is a continuous process, as we just saw. The early air gets heated up. So, we have to bring in more air. So, on a continuous basis, cold air is brought out to create film on the blade surface, on both the surfaces really, and finally, of course, certain amount of air may be brought out near the trailing edge to cool the trailing edge area. So, you may bring out the trailing edge air through the trailing edge or through some holes near the trailing edge, which creates film over the trailing edge to cool the trailing edge area. On the blade over here, which of course shows a 3-dimensional picture, you have two large internal passages, one passage over here, another passage over here, which of course exits the flow through the trailing edge. Many of the modern turbine trailing edges are indeed not rounded, but truncated like this, or sometimes straight away blunt, to allow this cold air to come out. So, this is something which requires very high manufacturing technology, typical for gas turbine manufacturing. And this is shown over here. You can see the discrete holes that are made over here on the blade surface, which allows this internal air to come out from inside onto the blade surface and create the films on both the surfaces, thereby cooling this area, which we have mentioned many times that it is an area that gets terribly heated up. So, you have a very elaborate cooling system, including film cooling that comes out over here and creates film, cold film over the surface. Then you have another row of blades, holes coming out through the blades, which create another round of film cooling. Then you have another row of holes again, through which cold air comes out, and a final row of holes near the trailing edge. So, they have calculated very accurately how many rows of blades are required and where on the blade surface in the clockwise position to create appropriate film cooling on this particular blade. So, this is how you create the cold film over the entire blade surface in a very accurate manner to effect effective cooling over the entire blade. This is a picture of a typical picture of a turbine blade, a modern turbine blade. This is the stator, this is the rotor, and as you can see, both the stator and the rotor have elaborate holes over the surfaces, which ooze out the internal cold air on the surface and create the cold film on the necessary on the surface to effect the cooling. As you can see, the stator has much more elaborate cooling technology. The modern blades also have, the rotors also have elaborate cooling technology on the rotor blades, rotating blades. So, this is the elaborate cooling technology that you need to do. Manufacturing these blades is extremely costly affair, and each single turbine blade is a hugely costly affair. It is entirely possible that one turbine blade one single turbine blade here could be costlier than making a whole set of compressor blades. So, that is how costly the turbine blades are, because they have embedded cooling technology inside those blades. Transpiration cooling, as we have seen, requires this is an attempt at a transpiration cooling. As we discussed, you have the porous outer shell, you require that porous outer shell, and then you have elaborate internal cooling passages, which has cold and compressed air, and those would be oozing out through these pores to create film cooling. So, you need a porous outer shell or a sheet to effect transpiration cooling, and this air of course, radially flows from hub to tip or tip to hub across the entire length of the blade to effect cooling over the entire length of the blade. Now, this is what I mentioned, that to the best of our knowledge, such porous technology, material technology has not yet matured, and to the best of our knowledge, that has not yet been applied commercially, even though lots of research is still going on in this area. A summary of the kind of technology that has been used over the years. As you can see here, in the early era, when it was only convection cooling, the advancement of compression ratio actually required that you can do with less cooling. So, as the compression ratio went up to 40, first 20 and then 40, you can see that you can do with less of temperature, because the relative cooling flow available from high pressure compressor allows you to put in more air flow, and as you can put in more air flow at high pressure, you can effectively do a lot of cooling. However, as the advanced cooling has been extended with film cooling, film and convection combined cooling, you can cool any blade from a pressure ratio of 5 to 40. 40 is a going high value of compression ratio. So, up to a pressure ratio of 40, you can keep on using the combined cooling system, and it can take you to temperature up to 2200. Transpiration cooling can give you even higher temperatures at a lower coolant film flow. So, the more and more advanced cooling technology you can deploy, you can use less and less coolant flow, because higher and higher compression ratio is now available, and then at each of those cooling passages you can pump in air at a higher pressure, and when you have that availability of high pressure air, you can afford to do with less and less mass of air, cold air, to effect effective cooling. So, over the years, as the pressure ratio has gone up, the cooling has indeed been facilitated by high compression ratio, and this is one of the advantages of the fact that compression ratio has gone up. The turbine technology has also effectively used higher turbine entry temperature. So, this is what has happened over the years. The two of them have gone up together. Let us look at what is happening when the surface temperature as felt. The film cooling only gives so much of relief. When you have convection cooling only, it gives so much relief, but once you have a combined film and convection cooling, the surface temperature comes down substantially, and this is on the blade surface. So, it tells us that on the blade surface, the temperature on the blade surface can be substantially lower if you have combined cooling system. So, only film cooling or only convection cooling actually does not give so much relief by themselves, but when you have combined cooling system, gives much more relief. And as we have seen in the earlier slide, you can actually do that even actually with less amount of air, because high pressure air is now available in modern aero engines. This is a picture again of a typical stator or nozzle cooling system. As you can see here, cooling air is brought in from here, it goes through these channels, it takes a turn over here, and then it takes another turn over here, and then it goes out through the tips. The other cooling air which is brought in near the leading edge goes straight out, because that is where cooling effectiveness is more, and then certain amount of air is impinge cooling on the leading edge surface itself. As we have discussed, this impingement cooling is going on, that air is finally also let out through the tip, and then certain amount of air is let out through holes near the trailing edge to effect trailing edge cooling, which again could be a hot spot. The inside surfaces of these cooling passages actually have turbulent promoters. The surfaces could be actually having small ribs or small bumps, as you have like speed breakers on a road. Those are, you can probably see them here a little, those ribs on the surface, that is to promote turbulence, so that the flow through these actually are actually promoted, and as a result of which the flow is facilitated. Otherwise, the flow may get impeded and may halt and may not be able to take this circuitous route to go through the entire blade passage. So, that needs to be facilitated through these ribs, which are on the inside surface. You can probably see them a little bit over here. So, that is the kind of passage that typically turbine blades have, and then they finally come out through the tips over here, which also does a little bit of tip cooling. The tips need to be cooled also along with the cross flow over the tip. So, it is elaborate cooling technology that is often used in modern hot gas blades. This was a stator blade. We can have a look at a rotor blade, in which the cooling technology is even more elaborate, because you need to have the blades are rotating. Remember, the flow inside will be feeling the centrifugal action. So, by centrifugal action, the flow will get thrown out outwards from here, as it comes in from here, and then that would facilitate that will give enough impetus to the flow to go through this channel and then finally come out through the tip. Same over here, it comes in over here, gets thrown out by centrifugal action. It will be promoted through ribs inside, and then through the passage it comes out and finally goes out. So, this is the up and down flow. It goes up here, it goes down there, and then it goes up here and goes down there, and then finally comes out through these slots to on the tips too. So, the amount of air, for example, which is going in here is 0.35%. The amount that is coming out could be as low as 0.03%. So, the total amount of air going is 0.76% of the main flow that is flowing over the gas, over the whole turbine, the entire gas flow. So, less than 1% of the main gas flow in terms of air mass is required for this elaborate cooling system. And if you have less than 1%, in the early era of cooling, the amount of air required used to be of the order of 3 to 4%, but now you can do with less than 1%. So, that much has been the advancement of cooling technology, and as a result of which, because of high pressure available, because of this entire manufacturing technology, the entire engineering that has gone into the turbine cooling technology has facilitated this entirely fascinating field of turbine cooling. It is a field by itself. Some people spend their whole life on turbine cooling technology. It is a fascinating field, there is no question about it, and it involves heat transfer, science of heat transfer, it involves aerodynamics, lots of fluid mechanics, extremely high technology in manufacturing and fabrication, and then all of it put together, best of all of them put together, gives you a cool turbine blade, and that is what you require to do a modern axial flow gas turbine blade. With this, we come to the end of our blade cooling technology discussion. You now know that a lot of technology is required to create a modern gas turbine blade. We will try to keep this in mind when we go into the next class, in which we will be discussing overall axial turbine blade design. We will bring in the blade design methodology into the next class, in which we will keep in mind that certain cooling technologies are available today, and with this we will see what kind of blades are being created for the modern gas turbines. They could be subsonic, they could be transonic, or we will see that we could even have supersonic blades for modern gas turbines. So, in the next class we will be looking at the design methodology of modern axial flow turbines.